Hello, everybody. Let us start our discussion today. Today, we shall introduce a very important tensor called the Riemann Curvature Tensor, and we'll look at its properties. We'll go on deriving a few things from it. The lectures are now going to be a little more mathematics oriented as it is required from now on. So let's start digging into it. What you observed last time, so let me remind you through some example, we observed a few things. We observed that irrespective of the coordinate systems, what we intuitively know as the flat manifolds like the the Euclidean 2D manifold, or should I say in the flat manifolds, in a closed loop, parallel transport, components of the vector doesn't change. And then we saw something interesting. We observed for, I say intuitively, curved manifolds, and this case the surface of the cylinder closed loop parallel transport keeps the component of the vector unchanged again. It's an intuitively curved manifold, but still nothing happens to the components of the vector. Even it never changes actually, as we saw last time. But for the surface of the sphere, there is change in general. And when I say change, this is the change of components of the vectors in a closed loop parallel transport. So though the surface of the cylinder and the surface of the sphere both are intuitively curved, we get completely different results there. Well, this is because we have to understand the curvature that we think of here intuitively is the intuitive curvature. This needs us to embed, or embed means see, the manifold into a higher dimensional space. Like both the cylinder and the sphere, we think of that it is embedded in the 3D Euclidean space of 3 dimension, and just we are dealing with the surface which is 2D, but it's embedded in one more extra dimension. And then we kind of see the intuitive curvature. So because this, to see this curvature, you have to go out of the manifold. This type of curvatures are called extrinsic curvature. On the other hand, just the notion of a closed loop parallel transport this happens all along in the manifold. And because it happens all along in the manifold, and we know that for a flat space this is zero, so the vector doesn't change, the components of the vector doesn't change in a closed loop parallel transport in a flat space. Because this happens now all along in the manifold, this let us measure the departure from let's say roughly flatness of the manifold. So this also will give us an idea of curvature, which I can actually measure being on the manifold. I don't need to embed it on an higher dimensional manifold. That's why this notion of curvature is called intrinsic curvature. And this is of importance in GR. It's more important in GR than the extrinsic curvature. So we'll learn about this intrinsic curvature today. Now to do this, we do, so we don't choose a manifold or a coordinate system now. So we look at an arbitrary manifold and arbitrary coordinate system. Okay, so now so far in the last lecture, we discussed 4 examples of moving around in the coordinate curves of a manifold and coming back to the same point. But now we want to make it more general, so we look at an arbitrary manifold and an arbitrary coordinate system. Just for simplicity, this we can go away with, and calculate it from starting with completely arbitrary curves. But for simplicity, and we'll generalize it at the last step, we choose to move around coordinate curves of only two coordinates. I can make a loop or make a closed loop coming back to the same point using at least two coordinates in a manifold. I may be able to do it with only one, just like we did for the two polar cases, but I need at least two. So I choose two. And this can be any two actually. That we'll do at the last step. That will elevate it to any two. But for the time being, just to distinguish it from the other ones, we call these as x1 and x2. So we'll move around x1 and x2 coordinates only. So the idea is the following, that so it's an arbitrary manifold and arbitrary coordinate system. So I'm just drawing these for cartoon purposes. So these are the lines where here in along this line the x1 remains constant. This is the coordinate line for x1. Along this line, the value of x1 is x1 plus delta x1. So value of the coordinate x1 in one case is x1, the other case is x1 plus delta x1. And this is one coordinate, and the other coordinates are these, where here the value of the x2 coordinate is x2, here the value is x2 plus delta x2. And what do I do? Let me draw it in the picture first. So this point I call P, Q, R, S. So you go from P to Q, Q to R to S, and come back to P. So that is essentially parallel transport along the coordinate curves and coming back to the same point. All that we have done so far works here. So we'll go case by case. So parallel transport. This is what we start now. So first we go from P to Q. For P to Q, what is constant? Well, when you are moving from P to Q, it is the coordinate line of x2. So x2 is constant. And the value is also x2. So let me write it this way. So I'll write for the, when I try to mean a coordinate, I'll write with a underline to that. The value of the coordinate x2 is constant. It is equals to x2. Value of the coordinate x1. This is my parameter, lambda, as we call it lambda. So then what is the transformation from P to Q? Well, I have never said that P and Q are nearby points, but let's assume that they are nearby points. So del A alpha going along changing is x1, so that's the parameter, plus gamma alpha beta 1 A beta is 0. Now the vector A, now let's see the notation. Vector A component alpha at Q. If I integrate this expression, remember again along this curve PQ, A alpha are only functions of x1, so I can change that delta to d. So I can do the integration, and this will be equals to then A alpha value at p plus the integration, keeping x2 equals x2 coordinate as x2, and the integration is over dx1. Okay, so it's basically you have solved the differential equation. If you wish, you have the two boundary conditions because it goes from p to q. At p, you know the coordinate values are x1, x2, and q it is x1 delta x1 x2. So you can do the integral, and this is what is the value of A alpha at Q. So I have parallelly transported the vector from P to Q, and I know what is the value of the vector at Q now. Okay, so let's do the next segment, which is Q to R. Where is Q to R? Q to R is this line, along this line, where, let's see, x1 remains constant. And what is the value of constant? It's x1 plus delta x1. And x2 coordinate is what changes. So that is I call lambda. So del A alpha, now x2 is what changes. So this is del x2 plus gamma alpha beta, now 2 A beta equals 0. We can again do the integral and write A alpha at now R equals A alpha at Q plus x1 as x1 plus delta x1 gamma alpha beta 2 A beta, and then integration is over dx2. Now let us look at this quantity. Then the thing in the integral. Thing in the integral is I have to evaluate it at the value of the coordinate x1 at x1 plus delta x1. But I can write this as x1 fixed to x1 itself, not x1 plus delta x1, the entire thing. And the little change that happens between the curve x1 equals x1, that is this curve, and x1 equals x1 plus delta x1. So I evaluate the quantity just like I do at basically Taylor series expansion of the second term. I say that it is equals to the value of the quantity at the curve x1 plus the first order Taylor series change between x1 and x1 delta x1, which is obviously delta x1 times the derivative of this. Now the derivative is with respect to x1 obviously, so it can come inside every as we are keeping x fixed in this dx2. And as you can imagine, A alpha r, now I can write in terms of A alpha q, because A alpha q I can replace from this So I can write this in terms of a alpha p, which is the original components of the vector. So I have one integral where x2 is fixed at x2 gamma alpha beta 1 a beta dx2 dx1 plus x1 fixed at x1 that integration is over dx2, and I need some space, so let's make some space. Now this integral, because we are approximating things to the first order, I can just do this integral and it will be delta x1 delta x2, because this integral is just over x2 now, and then I have del 1 of this entire thing. Let's keep this in a bracket. Okay, so that's the entire Q to R. Let's go from R to S now. So R to S. Let's see what it is. So as I go from R to S, you see that the coordinate changes the opposite direction of the parameter. And because of that, it will be just like P to Q, but now with a minus sign. And in R to S, x2 is constant as x2 plus delta x2. So let's see. So R to S, lambda is just like here, is instead of x1, it is minus x1, or minus lambda is x1, and x2 is fixed at x2 plus delta x2, del a alpha parameter is x1, and here I will get a minus sign because of that minus sign over there. And once I again try to write down a alpha at S in terms of a alpha at R, it will be exactly similar thing. Furthermore, I can do the same Taylor expansion here as we did before, and that will give me I have definitely a dx1 here. Let me write it directly. This derivative now will be with respect to 2. Okay, and the final leg of the journey is S back to P. Let's see what it is. S back to P, the coordinate that remains fixed is x equals to x1, and what changes is x2, and x2 changes in the opposite way than the parameter. So what I have here is x1 is constant now. The value is x1 itself, and x2 is minus lambda. So del A alpha del x2 minus beta 2 A beta is 0. Once you do the integral, you get. So this is, I call it prime because this is after the full uh, closed loop parallel transport. This equals to S minus, which also means that A alpha prime P is A alpha. S I replace from here. So this is R. I have x1 constant, this with x2 constant, this, and that extra term, well, which will come out to be all effective, all important term. And A alpha R we wrote down here in terms of A alpha P, so you can make the loop closed. We can write essentially, so let us write A alpha R in terms of A alpha P here, because otherwise it will be a very long expression. So these two are just equal and opposite of what I have before. Then I will have delta x1, delta x2, del 1 now. This term is essentially same as, so this term derivative with respect to 1 and gamma downstairs you have 2. Okay, so now if I call this as delta A alpha, which is the final thing minus the original thing at P, this you see is delta x1, delta x2, del 1, which I can now simplify a little bit and write delta A alpha is delta x1, delta x2. Let's do the derivatives inside. So this will be alpha beta 2 comma 1. I'm using Leibniz rule essentially. And let me write what comes from the other one first. Similar term. This also comes with A beta. And then I have so I get del 1 A beta here minus gamma alpha beta 1 del 2 A beta. One more step. Or maybe two more steps. You see, del 1 A beta is because it's being parallel transported, del 1 A beta can be written in terms of the corresponding gamma when it is parallel transported. So remember that for parallel transport or along such coordinate curves, del 1 A beta is same as minus of gamma beta some eta 1 and A eta. Similarly, this I can write as gamma beta eta 2 A eta. So what do I get? I get delta A alpha equals delta x1 delta x2. Let's see if I take the A beta also outside. The first two term doesn't shout because of that. They are happy. For the third term, you see that both beta and eta are dummy variables. They are summed over, so I can interchange them, which means I can write eta in terms of beta, and I should have started with the minus sign here. Let me do that. So I can write eta in terms of beta and beta in terms of eta. And then I get a beta, which I have taken outside, and I have this term. Again, I do the same trick here. Okay, now you see, we said that we are choosing the two curves, two coordinates 1 and 2 for our coordinate curves, but we could have chosen any of the coordinate curves, which means now I can, once we have done the calculation, now we can change 1 and 2 to say the index mu nu. Then I get a more general expression, which is delta x mu delta x nu A beta, and let me write it here as alpha beta mu nu, where I have traded for alpha beta mu nu, I have traded this entire expression, which involves the derivatives of the Christoffel symbol and its multiplications. Try to write this down for a few times. You will see a nice way of remembering it. This is called the Riemann Curvature Tensor. It's a tensor. So remember that if all components of a tensor is 0 in one reference frame, it must be 0 in all reference frame. And that is the case where we say that the manifold is not curved. So what is the type of this tensor? This tensor has one contravariant and 3 covariant indices. So it's 1-3 type, and we can write this as, so if I write it in a normal non coordinate basis, so remember that it has 4 slots, 1 form and 3 vectors. if it is written in this way, the way we have written the first index upstairs, then the first slot is for the one form and the rest of the slots are for the vectors. Right? And if I put in these slots, for the one form I put an unit one form, for the vectors I put unit vectors, I get the components of it in those bases. And now R can be written in terms of its components. Right? So this is our regular things. And apparently, because it's a tensor of total rank 4, it has 4 to the 4 components in 4 dimension, which is as large as 56. So let us, once we have defined this tensor, so this is the tensor. Let us summarize a little bit here. Maybe we are going a little fast. So this is the expression which told us how the vector, the components of the vector changes in a closed loop curve. And if all the components of the Riemann tensor is 0, then the component of the vector will not change. On the other hand, if at least one component is non-zero, then the components will change. You'll see that it is not possible to have at least one component non-zero, but that's a different issue. Riemann curvature tensor tells you if you go around in a manifold in closed loops in different ways, how the components of the vector changes. It's more interesting. You see, you go around in different loops, the components of the vector as you come back to the same point changes depending on the value of the Riemann curvature tensors, or these functions, all the components at that point where you come back. That's quite interesting. Okay, so let's look at some of the interesting things. One is, we ask the question, does the covariant derivative commute? Does it commute? What does it mean? It essentially means if I do two covariant derivatives of a vector a mu, is it equals to, put a question mark here, which means that we do not know whether this is true, the covariant derivatives taken in the opposite way. How do I calculate this? Well, let us calculate what is this quantity. Now this quantity is, to calculate this, let us first do the outside covariant derivative first, which is nothing but I do del x alpha of grad beta mu. Remember that this quantity is a mixed tensor. So there will be two terms in this covariant derivative. One will be when I take the contravariant index, and for the covariant index, I will have sorry, this is mu and this is alpha and beta. All right. So just revise how do you write down the covariant derivatives. This is straightforward. Now what I do is I want to break down the individual covariant derivatives here. So let me start from here because it's going to be long. This derivative is first a second derivative on a mu on x alpha x beta plus del x alpha of this minus okay, so that's all that you have in these. I still have to take the derivative of the second term, so it will be even bigger. So let me do that. I will start writing down things in short form. So this is essentially that. All right. Let me write the similar terms first. And then I will have these two terms. And okay, so now we can write down gamma beta alpha a mu, but obviously I have to write down so many terms there. So let us see what will happen if I write down things. Or let me write it down, because that is always, long term is sometimes easier to follow. So this is the quantity that we are interested in. What all I have to do here is to interchange alpha with beta and write down the same thing. Now the first term, if I interchange alpha with beta, nothing happens. Its partial derivative commutes. So I'll just write it that way. Then, if I interchange alpha with beta in the second term, this is where I have done it wrong. So this should be a eta alpha. I should properly write the indices. And the same mistake I have done a few times. As I can see, this eta and this mu should go upstairs. I think rest of the places I have done it correctly. Alright, let's come back. So I have A eta alpha, gamma mu eta beta, and then I have A eta beta, gamma mu eta alpha. Now as you see that if I interchange terms here, these two things just change their places. So I will just write them where they are. Both of the terms will be present in the new one. What happens if I interchange alpha beta here? Well, it remains as it is, because remember, the connections that we are working with are symmetric in their lower indices. So it remains as it is. So is this term. That also remains as it is. Or let us write this as beta alpha. It looks like we have almost every term similar, but then you realize that that's not quite true, because this term is completely different. This becomes A eta gamma mu eta alpha now, then beta. And this last term is also different. This becomes so what happens if I subtract one from the other? That is essentially checking whether this is true. Now let's calculate that. Clearly, everything will cancel out, only the terms written with blue or underlined with blue will remain. So let us write those down. I have A eta, and let me take A eta outside, at least forcefully for the time being. Let's see what if we can write everything in terms of A eta outside. So mu eta beta. See, eta is a dummy index at least here. Here also I can take A eta outside easily. But then when I write this, you see delta and eta are both dummy indices. I can interchange them. So delta, if I make eta, then it's fine if I take that outside. And finally, this term. What is this thing in the square bracket? Well, if you look back, it is nothing but the Riemann Curvature Tensor. First thing you realize is that we have to be careful while you take successive covariant derivatives because they don't commute. You cannot take one and take other later. You have to maintain the order. Second thing we realize is that the difference is given by the Riemann Curvature Tensor. This is sometimes written, this is a short form which we have sometimes introduced. For antisymmetry, we write alpha beta this way. Antisymmetry means essentially alpha beta minus beta alpha. So this is sometimes written as this way. So you see that Riemann curvature tensor also give us the difference between successive covariant differentiations. So let's look at some properties of R. Now, as you can imagine that it's a quite complicated an object, so it will be very difficult to look at its properties in an arbitrary system. But if we can find properties in terms of some equations, then as you say that those equations, if we find in any coordinate system, because they're tensor equations, they should be valid in all coordinate system if they are tensor equations. So what we'll do is we will write down the Riemann curvature tensor in local inertial system or flat spacetime. What happens in local inertial system? In local inertial system, the Christoffel symbols vanish, but the derivatives do exist. So which means the curvature tensor will just be the two derivatives of the Christoffel symbol. So local inertial system are alpha, beta, mu, nu is only are alpha, beta, only this much. And this is quite easy to remember. Can we write it in terms of the metric? It will be more useful. So let's try to write it in terms of metric. For that, let us look at one piece by piece. So first this piece. First, we'll write down the entire Christoffel symbol, which is G, say alpha eta, and this will have a derivative with respect to mu. Now, when I write this down, what I do is I write down the last term first, which will take for G the indices of the lower indices of the Christoffel symbol and derivative with respect to eta. Now I have G beta eta nu plus G nu eta beta. and this will have minus sign. Now, because we are dealing with local inertial difference frames, the derivatives of g's are 0. So in the Leibniz rule splits out this g. There is no derivative with respect to it I have to consider. So this simply becomes okay. Now what all I have to do is local inertial frame again. See, I have derivatives, and the derivatives do change if I go from local inertial to the general manifold, general frame. So I have to mention or remember this all the time. So what will this be? We'll have g. This I can take common because it doesn't have mu nu, which is what is changed. First term, the corresponding term from the second one here will come with a minus sign because I have a minus sign, and the nu and mu interchanged. And finally, nice. If you look at the first two terms, they are the partial derivative of the same thing, and the partial derivative, the order doesn't matter. So these two will cancel out. And what I will be left with is, again, let me again remind you, only for the local inertial frame, this is not a tensor equation. Okay, again, only in local inertial frame. And I can, because again, g can be taken inside the derivatives. In local inertial frame, its derivatives are 0. What I can do is, I can bring down one of these indices by multiplying it with another g. So this, I can write the following tensor. Let's look at the symmetry of this. So I have R alpha, beta, mu, nu. Let's ask the question, what happens if I interchange the position of alpha and beta? Okay. So if I interchange the position of alpha and beta, so I have this. If I interchange, it will become beta nu alpha mu, which is here. So these two will change places, which essentially means that at least with respect to these two, one will acquire a minus sign. What about the other two? Well, again, if you change alpha and beta here, you will get this because the metric is symmetric and the partial derivatives are symmetric. Which means if I interchange alpha and beta, it is antisymmetric with respect to the change of the first two indices. You can verify that it's also antisymmetric in the change of the last two indices. So I keep the first two fixed in this case and change the last two. And a more non-trivial one, which you can verify just writing down this entire thing, is that I keep alpha where it is in all three of them. There are three of them, and cyclically change beta, mu, and nu. So now nu comes first, and then beta mu, and then mu comes first, and then nu beta. This is equals to 0. All these three can be verified using the expression of R in local inertial frame. But interesting thing is, once you verify them, these three, what I have written down here, are tensor equations, which essentially means though they are verified through the local inertial frames, these identities given in terms of tensor equations they're valid in all reference frame. And I will write down one more identity and stop for today. It's called Bianchi Identity. And I also will not prove it to you. You have to prove it by yourself. Again, you can try to prove it in the local inertial frame where it is easier to prove. So in this case, it will involve three of the R, and the first two indices will not change its place. And then I'll consider a covariant derivative with respect to some other coordinate, say lambda. And then cycle over these last three coordinates, which I have written a little separately. This is the Bianchi identity. And just like before, I can write this as shorthand notation. If you have done electrodynamics, you might have encountered a similar thing in electrodynamics, but I will not tell you what it is. You should figure it out. All right. So that's it for today. We have looked at the parallel transport of a vector in an arbitrarily closed curve and introduced the idea of the intrinsic curvature given by the Riemann curvature tensor and looked at its properties. We'll continue from there in the next class.